In this course, we're going to discuss performance in terms of two different metrics. The first one is time, and the second one is space. Predominantly, we'll focus more on this time aspect than the space aspect. And why we care less about space is because of Moore's law. I don't know if you have already studied Moore's law or not, but it's a famous law by the founder of Intel who basically stated that the technological power or the number of transistors roughly doubles every 2 years. So this is a famous law by Gordon Moore, who is one of the pioneers in semiconductors. So he stated that because of this law, the cost of the computing power will basically decrease over the number of years because the number of transistors basically increase. So that yields to a lower cost of manufacturing the systems processing power. But we still care about time. And why is that? Because time is a key differentiator across products. Like, let's say if you were using your uh, touchscreen phone, and if it wasn't responding for maybe there was a lag of 1 second, you would automatically switch to another phone because you'll feel that the phone doesn't feel good. It doesn't provide you a good user experience, or it is not just fast enough. So it's definitely like frustrating. So that's why we care more about time, because psychologically we have this habit that once we get used to a particular algorithm working very fast, which is now the bar has been set that you can search a particular information on Google, let's say in less than a second. If now you have to search that information in more than 10 seconds by a competitor, you would just go crazy and move on to some other thing rather than searching that particular information. So a question arises is, why do we care about algorithmic analysis? And there are four particular big categories that I feel why we should care about it. Some of you might think that we should care about it because it's always good to know like whether our algorithms are correct, which is absolutely correct, or we get the satisfaction, or we are basically enjoying when we are analyzing these algorithms. For some others, it might be the value might be in experience, which is some algorithms are fast enough, so they give us better user experience, which I just described in the previous slide. The third one is the selling cost, which is the cost that typically businesses have, which is the cost of the product or the USP of the product, which allows more users to adopt a particular product. So algorithmic efficiency can allow more users to sign up for the product, or if it's bad efficiency, they can always switch to another product. So it's a key um, selling point for the companies. The last one is the cost to the companies. So let's say an algorithm takes a lot of data to store, which is a lot of memory to store that particular information. That might lead to more cost to the company, or the cost can also be in terms of the users that might move to another product or might join some competitor because of lower performance. So these are the four reasons why we should focus on algorithmic analysis. And that's why I'm like trying to motivate you why this topic is really important. It's not just because you want to get a job in the company, but this is like a key differentiator of different companies as well as products, or the holistic user experience that a user gets in terms of any particular software. I'll give you one more simple example, and then we'll move on to the different ways of analyzing a program. So this is a simple example, which is I requested the data that is stored by Google. This data could be the location data from my cell phone, or the maps data that Google stores, or through various cookies. Also, it includes some data in my drive and stuff. So when I requested that back in 2018, I discovered that Google stores roughly like 9.7 gigs of data. I tried to download it. It's like full of JSON files and stuff like that. So the key point I want to make is I'm not a power user, which is I don't store a lot of data on Google. So roughly, I have like around 10 gigs of data. Typically, there are about 2 billion active users of Google every month or at any particular moment of time. So even if 10 gigs is a big number, let's consider every user storing just 1 gigabyte of data, which is pretty normal because there might be some power users who are storing like terabytes or gigabytes of data buying like storage from Google, while there might be some users who might be just storing like 100 megs of data. So let's say some users, on average, a user stores 1 gigabyte of data. So the total repository of Google, this is just excluding all the web data as well as other files and stuff, is roughly 1 gigabyte into 2 billion, which is 2 into 10 to the power 9. If you translate this number, this is roughly equal to 2 exabytes or 2 into 10 to the power 18 bytes of data. You can also, like, if you're more familiar with terabytes, this should be 10 to the power 12. So about 2 million terabytes of data. That's roughly the repository of data that Google stores. Now, let's say a common operation that Google might have is to search that information in all the repositories for some reason. Like, let's say if it wants to find out the files, it wants to consider all the users and want to find some information from all the repository data. The like just like in the previous problem when we discussed duplicates in a list, how can we search information? We can search information by using two algorithms you already have learned in CS1, which is linear search as well as binary search. So linear search is searching linearly across each element, and binary search is something where you have an array or some sort of data and you divide it into half. You look like the data is sorted, so you look into either half, bisecting into the other half. If the data is not there, you just move on to the right of the middle or to the left of the middle if the data should be on the left based on the sorted nature of the list. So if you do a comparison of how much time would this calculate take for Google to search an information based on this particular size, uh, you'll find out that you need a metric to evaluate the performance of like how much time would this take. And what I mean by the metric is how much operations does the computers that are used at Google use. So I don't know what type of computers they use, but like let's say if we typically consider our laptop, they execute about a billion instructions per second, which is if the processor is 1 gigahertz. Uh, you'll learn about all these details in computer organization, but I just want to state that if it's 1 gigahertz, it's roughly about a billion operations per second. So in order to linearly search this data, which is 2 million of terabytes, if for one particular byte, it takes about um, for in 1 second, it can just do 10 to the power 9 bytes or 1 gig of data. This would typically take on the order of about 100 11,574 days to perform the linear search. I did some math, um, and then if you want to do that the same with the binary search, it would take about 31 seconds. So you can clearly see the difference. Like the linear search would take about approximately 31 years. I don't think anybody would have the time to wait that long to find some information. So binary search is the way to go. Of course, there are different optimizations that Google might be doing or using different data structures like hash maps and stuff, which we are going to discuss in the second half of the course. But the key argument here is that algorithms do matter, and because they can reduce the size of the execution times by a huge chunk. So the last thing I want to state in this video before we start with the three different ways to analyze our algorithms is the questions that you need to ask when analyzing different programs. And the three questions that you should always ask whenever you are evaluating an algorithm or creating your own programs throughout this course is how much time will this take? How much space does this consume? Which is how, like, can I do this better in terms of space or time performance? A lot of universities teach you with just these two things, which is thinking about the time and space. But I want to also encourage you to think about the third thing as well, which is, are there any patterns in data? Like whenever you are creating an algorithm, you need to consider, like, let's say if it was binary search, a pattern is the data is sorted, or when we are talking about lists, a pattern is the list is sorted. So you can create an algorithm based on the patterns of data that might be more optimized than another algorithm which cannot be performed if the nature of the data was not present. That's pretty much it. And then in the next video, we are going to discuss the three ways of evaluating this performance.